Welcome, everyone. I'm very happy to share our experience in applying reinforcement learning on large-scale power networks. And I will give a brief intro to current grid challenges first. We will focus on grid congestion management and actions that the operator has at hand to mitigate these problems. And my colleague Matthias Dorfer will then dive deeply into about grid operations planning and demonstrate the potential of such agent-based AI systems on the grid. Before that, allow me to say a few words about our company, enliteAI. We are a machine learning technology company where I have the pleasure to work with a team of exceptional researchers and engineers. And looking back at more than 45 AI projects over the last 5 years, we felt confident enough to work on deep tech topics that a company of our size would usually probably not address, focusing on technology, reinforcement learning, as well as on geospatial AI. So much to enlighten. Let's start with some statistics on the development of renewable energy. So what you see here is the newly installed generation capacity per year globally. With more than 300 gigawatt new generation capacity in 2020 alone, which is an impressive number by itself. But even more remarkable is that more than 80% of new installations globally is already renewables. So this is certainly extremely encouraging from a climate as well as a geopolitical perspective, but it is definitely challenging for power grid operators, which becomes pretty obvious if we, for example, look into the generation profile of wind and solar power in Germany over the course of 1 year. So there is some regularity in there. So solar power is yellow and of course produces daily spikes. We also see that the wind generation includes seasonality, which is green, and also varies greatly depending on the weather situation. And this immense volatility combined with the sheer amount of renewable generation power that is currently being integrated in the grid forms a very challenging environment for power networks. And in the next slide, we will see the main challenges. So first of all, we need to cope with this variability, which is not only confronting grid operation with very large power gradients, but also forces day ahead and intraday operation planning to be continuously updated with a large, let's say, additional source of uncertainty. We heard more about the background there already in another talk this morning. And less restricted energy markets have also increased cross-regional trading, of course, but this also results in longer distances the electricity travels on the grid. And TSOs are, for example, struggling to meet the ambitious 70% interconnection capacity target that was set by the regulator. And this trend is amplified by large-scale installations of renewables in specific regions, like, for example, offshore wind parks, which we see in this toy grid example to the right, with large wind generations in the north, and the largest consumers and zonal interconnections in the south. So additionally, an increase in electricity demand is forecasted with e-mobility and heavy producing industries switching their primary energy source to grid electricity. So what are the problems that we see in the grids? In our toy problem to the right, the economic generation dispatch with the offshore wind park at full power and additional energy being exported would lead to an overflow on the red line. And this is a extremely simple example of a grid congestion, which obviously requires a change in the power flow to really realize a secure grid operation within the operational constraints. And a typical way the standard way to solve this is to reduce the power generation on one side of the congestion and to ramp up the generation on the other side. So in our case, we would fire up a thermal generator, and this however comes at a price, and we lose renewable energy, and we are increasing emissions and introducing additional costs in the system. Another problem is grid stability. So large power gradients and limited predictability make it very difficult to maintain the high levels of grid availability and reliability that are demanded. And safely navigating these dynamic grid environments is very challenging already. And unexpected events, so-called contingencies, might leave very low tolerance to choose the right remedial action sequence to restore a safe operational state. But let's come back to AI and see how it can assist the power flow control in the next slide. You can recognize the two challenges described in the previous slide. So the first one, making the grid adaptable with efficient economic avoidance of grid congestion. And the second one being resilience, so identifying strategies to keep the grid stable, even if unexpected events occur in difficult and dynamic situations. And the same methodology can also be utilized for optimal risk-aware maintenance planning, as planning for outages became also more challenging in dynamic grids. And these three use cases are today ready to be brought into production use. Looking a little bit further into the future and looking into the bigger picture, we see the vision is of course the control room of the future, and it is not the goal to add yet another screen to already complex control room. Instead, the operators should be freed of the unnecessary cognitive load that's caused by supervising all these different subsystems. And the vision is to build an AI assistant with a more advanced interaction model that is able to present contextualized information and to work with attention mechanisms, and with the ultimate goal to create an augmented intelligence layer for operators. But so far we kept the discussion at a pretty abstract level. So now it's the time to dive a little bit deeper into the topic by looking at the specific actions. So the direct way to control the power flow is to change the generation of the load, obviously. And this is done with redispatching, used routinely by all grid operators, just shifting loads, shifting generation geographically. Renewables can't be redispatched in the same way as conventional generators, but if there's no other technical possibility, then production can be cut if necessary, and this is called feed-in management. But we of course also need to supplement the energy that is lost. On the other side, we have the demand side management, which is a big topic on its own, where the let's say orchestration of commercial and residential consumption can relieve the grid with and with load shedding being the ultimate measure considered only in the most critical situations. All those measures come at significant cost for the grid operator, which he has to pass on as network charges, of course. But there's a second class of flow control actions, which does not just change the input and output flows into the system, but also adjusts the configuration of the grid itself. For example, substations internally use bus bars that can be configured quite flexibly to, let's say, rewire the incoming and outgoing transmission lines. And in the simplest case, this switchgear can be used to switch off certain lines. But we can also split selected buses as a flow control measure, and to reach a more stable and balanced grid operation condition. Specialized power devices are another way to alter the flow to reduce the need for costly redispatching measures, but the associated investment costs limits the number of such installations. Topology changes and power device actions don't produce any external costs, so this is the reason why these measures are called non-costly measures. And looking at this cost difference, it almost looks a little bit too simple to be discussed. Clearly, grids would exhaust all non-costly measures to cope with congestion and contingency violations and only turn to costly measures in extreme cases. But here I will hand over to my colleague Matthias Dorfer to explain to you why the potential of non-costly measures can't be fully realized by grid operators.
Yes, thank you, Marcel. So we have now heard that there would be really nice, fast and economic measures available to stabilize grids. But why is it that they are not used more broadly? So one of the reasons is it's controlling the grid topology actively is a complex and hard task. And now, why is it a hard task? So what we see down here on the left is a small-sized power grid with all its components. These are loads, these are generators, these are power lines and substations. And if we now pick, for example, a substation, what we can control on such a substation is the bus bar to which a certain power line is connected to. And this implies that the power grid configuration that we see on the bottom left is not the only possible grid configuration, but there are actually many, many of these configurations. And with a growing grid size and growing controllable count of controllable components, the number of possible grid topologies actually grows exponentially really, really fast to an astronomical number. So now controlling the grid topology or optimizing the grid topology would be in principle a classical mathematical optimization problem. But due to this astronomical space of possible solutions, addressing this problem with these class of methods is not feasible. So if we now step back a little and look into a different optimization domain, namely in the AI-based optimization, then there is a particular class of algorithms which has really proven superior performance when it comes to combinatorial optimization in the last years. And this is the class of AlphaGo or AlphaZero algorithms, originally developed for strategic board games and for planning strategies in these games. If we now again go back a step and look at it from a combinatorial optimization point of view, optimizing the grid topology isn't actually that different, except for, of course, uncertainty and other regulatory things. But in its essence, optimizing the grid topology is not that different to finding an optimal planning strategy in such a strategic board game. And so the key idea of our solution is that we extend the reinforcement learning algorithm AlphaZero to apply it to operation planning in large power grids. So how does this reinforcement learning look like? Before we take a closer look, I would like to draw a distinction to supervised learning, which is the machine learning paradigm that we usually think about when we talk about machine learning or artificial intelligence. So in the beginning, there is always, in both cases, the data. So we have our live grid and we record historic data from this live grid. Now, given this historic data, we can, for example, train with the supervised learning model. We have seen a couple of examples in this class already today, a predictive forecasting model for our loads, for renewables, for congestions, and so on and so forth. And once such a model is trained, we can use it as a decision basis for our daily work routine. So what we do is, from a machine learning and AI perspective, conceptually very different. We still leverage the historical data, but instead of directly training a static model, we use the data to engineer a simulated grid that can be somehow seen as a digital twin of the actual live grid. And now, given this simulated version of the live grid, we can now develop and train a reinforcement learning agent which learns its behavior by interacting with the simulated grid, by first receiving the current state of the simulated power grid and then taking appropriate actions in response to the current state we are in. In our case, these are topology and redispatching actions. And what we now will end up is not a predictive forecasting model, but we will end up with the interactive grid operation decision support system that can suggest topology correction and redispatching actions to human operators and support their daily work routine. I noted here topology and redispatching actions. In the next couple of slides, we will only take a look at topology action. And so we will also skip the entire training and development process and just assume that the agent is already trained, and we will now take a look at the concrete example what such an agent is capable of. So first of all, we have here the power grid we have already seen before, and there is an expected congestion on this power line with a load of 148%. So as Marcel already pointed out, in the traditional congestion management manner, we could now see if there are generators, for example, this one that is fueled by fossil energy, and we could try to ramp these generators up or ramp them down in order to mitigate this congestion. But there is a nice and fast and economic alternative, actually. And let's see what our agent suggests here. So the first action that the agent suggests is a bus split on substation 28. And we can already observe with this simple bus split, we can distribute the overload on originally on this power line to these two neighboring power lines. And if we now look at the second action, which is another bus split on substation 34, we can see that this overflow already drops and one congestion has already been mitigated. And lastly, we can take a final bus split on this substation here, and we can see that the overflow, the original overflow on this power line has been prevented without any redispatching or whatsoever. So this is a really nice solution to this expected congestion, but how does the agent actually find such action sequences? And well, the answer is by leveraging a large-scale AI-guided topology tree search. And since this is an applied artificial intelligence conference, let's just dig a little bit deeper into the inner workings of this search routine. So what we see here is the root node of such a search tree. In our case, this is the original initial grid state. And each node in this tree will be either an actual power grid state or a future simulated power grid state. And for each node in the tree, we will also compute a full power flow computation as well as a contingency analysis. So we have here our initial grid state with the congestion, and we will now start the topology tree search. As I said before, brute force search is not feasible because the search space is astronomical. So we will guide the search process into promising directions with our AI agent. And if we expand the search tree now for one hierarchy level, we can see now that next to the root node, we have now our future simulated grid states. And the edges in this search tree are actually actions that the agent suggests to prevent this congestion. And in this case, it's the bus split on substation 28. And this state then corresponds to the future grid state that we have already seen before in the action sequence. And we can now unroll this entire tree. And what we will end up with is, for example, this path here, which can be seen as an action plan or operation plan that should prevent the upcoming congestion. And since we are performing a tree search, we will not only have one of such paths or operation plans, but multiple of those. We can also see that some paths won't be that promising, but that's in the nature of the problem, obviously. But what we now do as a final step in our methodology is that we take the viable scenarios and re-evaluate them with regard to the complexity of the solution. So, for example, we would like to keep the number of required remedial actions as low as possible. But we also consider congestion management costs. So is there, for example, redispatching required on top? And we also perform, of course, a contingency analysis and see if these paths are actually executable in the live grid then. So this is basically, once the agent is trained, the methodology in a nutshell and shows how it can be applied. And we will now take this methodology to a bit more elaborate example. And we will in particular look at the congestion management scenario in a day-ahead planning-like scenario. So what you see here is a variant of the IEEE 118 grid with 118 substations. And we will look at the evaluation period of 1 week. So what we now will do is, and this is our baseline and our first step in this analysis, we run for this entire week a complete power flow computation based on the predicted forecasts that we got on a static grid topology. So no active topology control is involved yet, and without applying any redispatching and counter trading. And what we see here now is that throughout this planning period, there are expected congestions upcoming. This is just the example image here for this congestion. This is obviously something that we don't want. So we will now take the classic approach and simply rerun the entire simulation period. But this time, whenever there is a congestion upcoming, we compute the optimal power flow to get the economic redispatch. And as we can see, when we do this, we are able to mitigate these expected congestions here. This is very nice from a grid stability point of view, but on the other hand, it also requires to ramp up the slow generators, and on top of it, most of the redispatching is often based on fossil energies, and we can see here that all of this comes with a substantial amount of redispatching in megawatts and corresponding congestion management costs. So this is obviously not nice. So what we will now do is we will run the very same planning scenario, but this time, before we apply redispatching, we will put our topology planning agent in place, and we will see if the agent finds solutions to the expected congestions and is now able to prevent this redispatching. And if we look at this curve up here, we can see that indeed we are again able to prevent all congestions. By the way, these dashed lines are points in time where topological corrections are suggested and applied by our agent. So as I said, we are able to mitigate these congestions here. But if we now look at the redispatching that is still required, this has been drastically reduced. And if we put these two things or these two approaches directly in contrast, we can see that obviously for this selected scenario, we are able to drop the required redispatching by almost 95%. So what can we conclude from this study? So first of all, topological corrections are a fast and economical option to add stability and flexibility to the grid. On top of that, as a non-costly congestion management measure, it can also significantly reduce redispatching costs. And yeah, as a side note, we of course have to take the example and the results here with a grain of salt, because the actual potential always will depend on the grid topology on the one side and also the energy mix that we are facing in the grid. Yes. So if all of this is interesting to you and you would like to get a better feeling for how such a system behaves, we warmly invite you to visit this URL here, where we prepared the very methodology that I just showed you in a gamified version, where you are basically the grid operator and you can try to solve 3 different scenarios, ranging from really easy to a very hard scenario, and you can just play around with this methodology a bit and see how the agent behaves. And Marcel, if you're ready, I would like to hand over for the wrap up to you.
Thank you, Matthias. Yeah, the distilled summary of the last 20 or so minutes. So we saw that everybody already knew, of course, that the energy sector is transitioning towards clean energy already with more than 80% of the global newly installed generation capacity. Then we saw that the volatility and fluctuations leads to grid congestions and other instabilities, and we can address these instabilities and congestions with topological corrections, which is a form of non-costly measures, and therefore bring back the stability and enable flexibility on the grid. We also saw that this methodology enables grid operation decision support systems, and as Matthias already showed you, there's a web demo. So please, if you're interested, give it a try. The QR code is to the right, and it's also a little bit intentional that the QR code is near the control room of the future picture because this already represents a small step, of course, towards this direction. This brings us to the end of the talk. Thank you. Happy to take the questions.
Thank you so much, Marcel and Matthias. This is really interesting, and we have, as I already said before, a very knowledgeable audience from the energy sector who sent us a couple of questions that we will have a look at right now. Ahmad.
Yes, first, thank you from my side. It's always nice to see real applications of reinforcement learning. So well done, guys. The first question is about the stability of RL models. So the question says, RL models could be unstable, and you mentioned AlphaGo in your presentation. So how to avoid random actions due basically to edge cases like the move 78 of AlphaGo, and to make more moves like the brilliant move, which is basically the move 37.
So yeah, Marcel, I think I can take this one. So first of all, when it comes, there are different classes of reinforcement learning. And the particular one that we have chosen is based on a tree search. And this already adds a lot of stability to the system, because we are in a certain state, we would like to find the appropriate action or response. And we now unroll a lot of potential possible futures. And in contrast to, for example, playing Go, where we have to stop this search process at some point, we can really search all these paths towards the end and evaluate how they will turn out into the future. And this evaluation includes power flow computation, as I said before, but also contingency analysis. So given these facts, we would never suggest or select the action that bears too much uncertainty in the future, but really evaluate if a path is viable and then only select these. So this is a bit different to the original setting of AlphaGo.
Thank you very much. The second question is, can one use RL for other type of networks? So not only Powergrid network?
Yeah, so I mean, we started out with power networks, of course, and as you probably saw from the terminology, so we started in the TSO world. So the first of all, this also the same methodology applies to distribution networks as well, and also, I mean, out of context of this conference, but there's no reason why it should not work for, I don't know, gas pipelines or watering distribution systems. So it's I mean, let's say the basic blocks are, we need to have a simulation available that's really as precise and as accurate as possible, and can be used during training and also for the stability issues that we just discussed. And yeah, we need to also that we can bring let's say the most effects when there is a large amount of different actions available at any time. So because otherwise, for a smaller action space, there are classical methods also available. Mathematical optimization works, but mathematical optimization breaks once we have many different options at any time step available.
All right, thank you. The second question is, what it takes basically for energy companies to adopt and getting started with your solution?
I can answer this one as well. So it's the first step always is to look into the real live grid and to model this first. And this is, fortunately, I mean, it's not, it's certainly not a coincidence that we work with this type of networks with reinforcement learning, just because the simulations are already there. So usually it's a question of converting the digital twins that are already available in one or another form, and of modeling different scenarios in the first step. And I would estimate this takes around, let's say, 2 months to get started, and another month probably to tune it a little bit to get first results. And of course, it's a longer process to bring a complex system like that really into production in all the different planning steps. But I would say first results are achievable within a time span of 3 months.
Great. And the next question is about your competition that you have won actually with this solution. What is different actually from your solution comparing to the other participants, and what made you win this competition or be in the top 3 in this competition?
Yeah, Marcel, then I will take this one again. So I would say one, or the biggest difference is actually that, so all of this began now 2 years ago, and we have been also developing our in-house reinforcement learning framework, MAZE. And back then we have been solely good machine learners and machine learning experts. And when we started working on the problem, the domain knowledge, I would say, was still missing, the particular domain knowledge for the energy sector. And the one key difference to other approaches of our approaches is that the solution that the agent comes up with are really solutions that the agent comes up with without injecting any domain knowledge or biasing the solution towards certain human intentions. This throughout the last year changed, of course, and we now, since we are now in the phase of applying this practically, changed, and we are now using as much as domain knowledge as possible, of course. But for the challenge submission, we really tried to come up with a general learning system that learns this behavior from scratch.
Great, thank you. And the last question is about explainability. So how do you tackle the problem of explainability in such scenarios? So for Powergrid, congestion.
And maybe, if possible, a quick answer.
Yeah.
Yeah. So the agent doesn't always have to be explainable. In our opinion, it's much more important that the solution is explainable and understandable. And the fact that we can roll out this search tree and we can show the exact solution step by step to the human operator allows the human operator to inspect if this is a viable path and then say, okay, I will accept this or not. So the solution per se is in front of the operator and explains what the agent would like to do. And I think this should be really helpful.